Tonight, we are going to dismantle an image that has been sitting in your mind since you first learned the name of this spacecraft. An image you have probably never questioned. An image that almost every documentary, every textbook, every science teacher has quietly handed to you. And it is wrong. You have heard the story before. A small probe launched in the 1970s drifting out of our solar system, tired, aging, whispering its last signals back to Earth from somewhere far away. A little machine that has, in the language we always use, left. Done its job, become the most distant human-made object in history, and now, slowly, gracefully dying. You have seen the diagrams. A flat picture of the sun in the center, the 8 planets in their neat little orbits, and one tiny dot labeled Voyager 1 sitting just past the edge. Out there. Gone. Finished. Forget that image. Tonight we erase it, because Voyager 1 has not left the solar system. It is nowhere near leaving the solar system. By any honest measure of where our solar system actually ends, it has barely stepped off the front porch. It has not even reached the gate. It has not even reached the long road that leads to the gate. And the journey that you think is ending is, in fact, the very first heartbeat of a voyage so long that the human imagination collapses trying to hold it. So tonight, the question we are going to ask, the one strange, almost unanswerable question that the next hour and 45 minutes will slowly orbit is this. How far can Voyager 1 actually travel? Not how far has it gone, not where will it be in our lifetimes, but how far in the absolute and the deep and final reckoning can this small piece of 1970s machinery, drifting silently through the dark, actually reach? And here is where it gets strange. Because the more carefully we look for an answer, the more the question begins to dissolve. The more the edges of it blur. The more we start to suspect that the question itself, the question you have probably asked yourself 100 times under a quiet sky, was built on assumptions that simply do not survive contact with the real numbers. Voyager 1 is not winding down. Voyager 1 is, by every honest measurement, just beginning. And what it is beginning is something so vast that you, and I, and everyone we have ever known will be long vanished dust before it even reaches the first interesting milestone. So before we go any further, if you find this kind of slow, deep exploration fascinating, a quiet like or a subscribe really helps this channel keep growing. It is a small thing for you. It makes an enormous difference for me. And it lets me keep making these long, contemplative journeys for you to listen to late at night when the world is finally still. Now, let us begin. Over the next hour and a half, we are going to follow Voyager 1 outward. Not just to where it is right now, in this very moment as you listen, drifting somewhere in the constellation Ophiuchus, more than 15 billion miles from the chair you are sitting in. We are going to go much, much further than that. We will start with the spacecraft itself. A strange little machine, built with computers weaker than the device in your pocket, weighing less than a small car, carrying instruments designed to last 5 years. We will see how this fragile thing was hurled past Jupiter and Saturn, and how a single moon, a hazy orange world called Titan, made a decision that would send Voyager 1 out of the plane of the planets forever. Then we will look at exactly where it is, right now, in the year you are listening. We will hear about the signal that takes more than 23 hours to reach it, about the engineer who sends a command on a Monday and waits until Wednesday to hear an answer, about the milestone that, in November of 2026, will make Voyager 1 the first object built by human hands to be more than 1 full day of light away from us. And then, the floor will fall out. Because we will discover that this immense distance, this distance so vast that even light needs a whole day to cross it, is not even the beginning of the journey. We will find out that the real edge of our solar system is not where you have been told. It is not at Neptune. It is not at Pluto. It is not even at the bubble of the sun's wind. The real edge is something else entirely. Something so far, so faint, so strange that Voyager 1, traveling at 38,000 miles an hour, will not even reach the inner boundary of it for another 300 years, and it will not pass through the outer boundary for another 30,000. After that, the encounters begin. A red dwarf star named Gliese 445, drifting silently toward Voyager 1 across 40,000 years of darkness. A second star, a third, names we have only known for a few decades, each one passed in the deep silence of hundreds of thousands of years. A slow exit from the cocoon of warm gas our sun is currently drifting through. And then, far beyond anything human language has a proper word for, the Milky Way itself begins to turn beneath Voyager 1 like a vast wheel, carrying it on an orbit 250 million years long. And by the time we reach the end of this story, we will have to confront something almost unbearable: that this small machine, made of aluminum and gold and plutonium, with 3 computers that share less memory between them than a single email, may very well outlive the Earth, may outlive the Sun, may, in some final calculation of the deep future, be the longest surviving artifact our species ever creates. A small, silent witness to the fact that once, on a tiny blue world, there lived a kind of creature that looked up at the stars and decided to send something of itself toward them. That is where this is going. That is what we are about to follow, step by careful step, layer by layer, outward and outward and outward, until the question of how far Voyager 1 can travel comes apart in our hands. And before we do anything else, before we measure a single mile of the road ahead, we have to start somewhere intimate, somewhere small, because the staggering distances that lie before this spacecraft only make sense if you first understand the spacecraft itself. The strange little machine that, almost half a century ago, slipped quietly off a launch pad in Florida and began this impossibly long walk into the dark. So here is something I want you to think about before we move on. Before this video began, before the first words you heard tonight, when you pictured Voyager 1 in your mind, what did you actually see? A satellite, a small probe, a tiny spaceship like the ones in science fiction, or just a vague dot somewhere out there, somewhere beyond the planets? Take a moment and leave it in the comments. I read them, I think about them, and I am genuinely curious what image you have been carrying. Because in the next few minutes, we are going to replace whatever picture is in your head with something far stranger, far smaller, and far more fragile than you might expect. To understand how far this thing can travel, we have to begin where its story begins. Not in the dark of interstellar space, but in a clean room in Pasadena, California, in the middle of the 1970s, where a strange, 10-sided machine sat quietly waiting for the sky. If you stood inside that clean room in Pasadena in the spring of 1977 and looked at the thing that would one day become the most distant human-made object in the universe, you would not be impressed. Not at first. It is not sleek. It is not elegant. It is not the smooth silver bullet of a science fiction film. It is a strange, 10-sided box, roughly the shape of a pill organizer that has been pulled out into a small, awkward decagon. A bus, the engineers call it. A flat-faced, 10-sided container, less than 2 meters across, draped in foil and wire and dark plates, with a great white dish growing out of one side like a single enormous ear. That dish is the high-gain antenna, 3.7 meters across, about 12 feet. Roughly the size of a small bedroom, tilted on its edge. And almost every choice that was ever made about Voyager 1 was made so that this one piece of curved metal could be kept pointed at the Earth. Because without it, there is no signal. Without it, there is no mission. Without it, this small machine becomes nothing more than a piece of falling debris, drifting silently through the dark, with no one ever knowing where it went. The whole spacecraft weighs about 825 kilograms. That is roughly the mass of a single small car with no passengers and an empty trunk. Out of that mass, more than 100 kilograms is the scientific instruments, cameras that no longer work, magnetometers that still do, plasma sensors, cosmic ray detectors. A long boom that sticks out into space, holding instruments away from the magnetic field of the spacecraft itself, so that it can hear the faint whisper of the interstellar wind without its own body humming over the top of it. And then there are the computers, 3 of them, each one a little different from the others, with backup systems, error correction, and the kind of careful redundancy that engineers in the 1970s built into machines they knew they would never be able to touch again. The total memory of all 3 computers combined is around 68 kilobytes. Not megabytes, not gigabytes, 68 kilobytes. The little phone in your pocket, the one you check 50 or 100 times a day, has roughly 1,000,000 times more memory than that. The processors on board Voyager 1 run at about 250 kilohertz. Your laptop runs around 10,000 times faster, your phone faster still, and yet, this is the machine that has, for nearly half a century, kept itself alive, kept itself pointed, kept itself talking, kept itself stable in 3 dimensions, slowly correcting its attitude with 16 tiny hydrazine thrusters, like a swimmer making small, careful adjustments to keep their face above the water. With less computing power than the cheapest greeting card that plays a song when you open it, Voyager 1 has navigated the deepest journey in the history of our species. Power comes from something stranger. There are no solar panels. The sun is too far. By the time you reach Jupiter, sunlight is already too weak to be useful in the way it is near Earth, and Voyager 1 was always going to be going much, much further than Jupiter. So instead, the spacecraft carries 3 radioisotope thermoelectric generators. 3 small canisters, each filled with plutonium-238. The plutonium is hot, it decays. The heat is converted into electricity. And that electricity, year after year, decade after decade, has kept Voyager 1 alive. But it is fading. With every passing year, the plutonium has less to give. The generators lose about 4 watts of power annually. 4 watts, the amount needed to dimly light a small nightlight. Not much in a single year, but across decades it adds up. And so, one by one, instruments have been turned off. Heaters have been switched off. Cameras have been silenced. Each year, the team that runs the spacecraft sits down in a small room at the Jet Propulsion Laboratory in Pasadena and makes a quiet, painful decision about what to let go of next, so that the rest can keep living. As of the year you are listening, only 2 instruments on Voyager 1 are still operating. The plasma wave subsystem, which listens for the faint song of charged particles in the interstellar wind, and the magnetometer, which feels the faint pressure of the galactic magnetic field. That is all. The rest is dark. The cameras have been off since 1990. Most of the other sensors are quiet. The spacecraft has been slowly stripped down to its essentials, like an old ship throwing furniture overboard to stay afloat in a long, slow storm. And yet, it is still listening. It is still feeling. It is still sending back data, at a rate so slow it almost feels insulting in the modern world. 16 bits per second going up, 160 bits per second coming back down. That is roughly the speed of the very first home modems, the ones that screeched and hissed in the late 1980s. Across the entire vast distance between us and Voyager 1, the data trickles in like water through a cracked pipe. Slow, patient, faithful. Now let us go back. Back to before any of this had happened. Back to the late summer of 1977, when this strange little 10-sided machine sat on top of a Titan Centaur rocket at Cape Canaveral in Florida, waiting for its moment. It launched on September 5, 1977. And here is the first curious thing. Voyager 1 was not the first Voyager. Its twin, Voyager 2, had been launched 16 days earlier on August 20th. The names are confusing, almost backwards. The reason is simple. Voyager 1 was on a faster trajectory, a more aggressive path. It would overtake Voyager 2 within months. And so the engineers, knowing this, named them in the order they would arrive at their first destination, not the order they would leave Earth. Voyager 1 was the second to launch. But it was always going to be the first to anywhere that mattered. It crossed the asteroid belt without incident, and by the spring of 1979 it reached Jupiter, the largest planet in the solar system. A world so massive that all of the other planets put together could fit inside it more than 2 times over. Voyager 1 took the first close pictures of Jupiter's storms that anyone had ever seen. The swirls, the reds and creams and pale yellows. The great red spot, churning slowly, a storm older than any country on Earth. It found new moons. It found a thin, faint ring around Jupiter that nobody had known was there. It looked at the moon Io and saw something no one expected. Volcanoes, active volcanoes. The first ever discovered on another world, and then it kept going. Onward, outward, deeper. By November of 1980, it reached Saturn, and here the story turns on a single, fateful decision. A decision that, more than any other choice in the history of the mission, defined how far Voyager 1 could ever travel. There was a moon at Saturn, a strange, hazy, orange moon called Titan. It was the largest moon of Saturn and one of the largest in the entire solar system. And from a distance, scientists could already tell that Titan was different. It had an atmosphere, a thick one, a real, opaque, planet-like atmosphere wrapped around what was technically just a moon. Nobody knew what was under that haze. Mountains, oceans, continents. Nobody knew, and here was a chance to fly close, to pierce the veil, to send back the first detailed measurements of an atmospheric world in the outer solar system. But there was a cost. To get close to Titan, really close, Voyager 1 had to angle its trajectory in a very particular way. The gravity of Saturn, used carefully, would slingshot the spacecraft past Titan and on to the next planet. But the geometry of a Titan flyby would not allow that. To go close to Titan, Voyager 1 would have to give up its chance at Uranus, its chance at Neptune, its chance at Pluto, all of them forever. A close pass at Titan would fling Voyager 1 upward, out of the flat plane of the planets, into a trajectory that would never bring it near another world again. The mission planners thought about it carefully, and they decided Titan was worth it. The chance to study that strange, thick atmosphere was, in their judgment, more valuable than seeing 2 more gas giants up close. Besides, Voyager 2 was still coming. Voyager 2 could be aimed at Uranus and Neptune. The siblings could split the journey between them. And so in November of 1980, Voyager 1 swung close to Titan. It measured the atmosphere. It found nitrogen, methane, a thick orange smog. It found that Titan was, in some ways, a frozen echo of the early Earth. And then, exactly as planned, the geometry of that flyby flung Voyager 1 up and out of the plane of the planets. Tilted at about 35 degrees above the ecliptic, the flat disk on which all the planets march around the Sun. From that day forward, Voyager 1 was no longer moving across the solar system. It was rising up out of it, climbing into the empty space above the great wheel of the planets. It has been on that exact same path ever since. The same speed, the same angle, the same direction, for more than 4.5 decades. No course corrections, no engine burns, no changes, just the silent, unending coast of an object that has been given everything it will ever need from gravity and now simply moves. And then before Voyager 1 left Saturn's neighborhood entirely, there was one more thing tucked onto its side. A small disk, 12 inches across, gold-plated copper, protected by an aluminum jacket, bolted to the outside of the spacecraft where any future finder could not miss it. The golden record. The story of how that record came to exist is almost as strange as the spacecraft itself. In the months before launch, the project manager, A man named John Cassani asked the astronomer Carl Sagan whether the Voyager spacecraft should carry some kind of message. Something for whoever or whatever might one day find them. There had been earlier attempts. The Pioneer probes had carried small metal plaques etched with simple line drawings of a man, a woman, and a map showing the location of Earth using nearby pulsars. The Pioneer plaques were small, modest. A whisper. For Voyager, Sagan wanted to do more. He had 6 weeks. The budget was $1,500. The weight allowance was small. The record had to be light. The format had to last. And what was placed on it had to somehow represent the entire diversity of life and culture on Earth. 6 weeks, $1,500, the whole story of humanity. Sagan gathered a team: the astronomer Frank Drake, the artist John Lomerg, the writer Anne Druyan, who would later become Sagan's wife, the producer Timothy Ferris, the ethnomusicologists Robert Brown and Alan Lomax. Together they began choosing, arguing, selecting, throwing things out, putting things in. What ended up on the record is almost too poetic to be true. 116 images. Greetings spoken in 55 languages, beginning with Akkadian, a language last spoken in ancient Sumer more than 5,000 years ago, and ending with Wu, a modern Chinese dialect. There is a printed message from the United States President of the time, Jimmy Carter. A message from the Secretary General of the United Nations. There are the sounds of Earth itself: wind, thunder, surf breaking on a shore, the songs of birds, the calls of whales, a human kiss, a mother greeting her newborn child, footsteps, laughter, heartbeats, and there is music. 90 minutes of it: Bach, Beethoven, Mozart, Stravinsky, a traditional song from the Solomon Islands, a bagpipe tune from Azerbaijan, Indian classical music sung by Kesarbai Kirkar, the blues of Blind Willie Johnson, Chuck Berry's Johnny B. Good. Someone on the committee argued that rock and roll was adolescent and did not belong. Sagan replied that there were a lot of adolescents on the planet. The song stayed. And tucked away in the middle of the record, almost as a secret, is 1 hour of the brain waves and heartbeat of Anne Druyan, recorded in a hospital in New York City just days after she and Sagan had impulsively decided, over the phone, that they were in love. She had a list of thoughts she wanted to think about during the recording: the history of philosophy, the agony and beauty of being alive, the terror of the late 20th century, the hope of love. All of it compressed into about a minute of data on the record, encoded as the rhythm of one woman's nervous system on a single afternoon in the summer of 1977. The record was gold-plated for protection, designed to last. Conservative estimates suggest the gold plating alone could remain readable for 1 billion years in the cold vacuum of space. 1 billion years, the age of the Earth, twice over, and longer than complex life has existed on this planet. And so, when Voyager 1 finally tilted upward and out of the plane of the planets, after Titan, after Saturn, it carried this small disk with it, a message in a bottle, thrown into a cosmic ocean. Bach and birdsong and a woman's heartbeat and a child's first laugh, fixed in gold, drifting outward into the dark. That is the spacecraft. That is what we are following. Not a sleek silver vessel, not a powerful starship, a small, fragile, 800-kilogram machine with the brain of a pocket calculator, the antenna of a small bedroom, the data rate of a 1980s modem, a slowly cooling lump of plutonium for power, and a gold record bolted to its side, carrying a single hour of a stranger's heartbeat into eternity. Take a moment with that, because the rest of this story, every staggering distance we are about to walk, every 1,000-year deep silence we are about to listen into, every star we are about to brush past in the long galactic dark, is being made by this small thing. This vulnerable, beautiful, almost ridiculous little machine, built by people in a clean room in Pasadena, who knew they were sending it somewhere they would never see, and who chose, somehow, to send a kiss and a heartbeat with it. So let me ask you something before we continue. If somebody handed you a 12-inch disc tonight and told you it would last 1 billion years, and that whatever you put on it would be the only piece of your species that some distant finder might ever know, what would you choose? Not what should be there in some grand official sense. What would you choose? A song, a voice, a photograph, the laugh of someone you love? Take a moment and tell me in the comments. I genuinely want to know. Because the people who chose for Voyager 1 had 6 weeks, you can take as long as you like. And once you have your answer in your head, hold it there. Because it is time to leave the launch pad behind. It is time to leave Jupiter and Saturn and Titan and the bright inner solar system. It is time to follow Voyager 1 forward across nearly half a century of silent coasting, all the way to where it is right now, in this very moment, as you listen. To a place so far away that even the light from your own house, leaving at the speed of light, would not catch up to it for almost a full day. Right now, as you are listening to my voice, Voyager 1 is moving, not metaphorically, literally. Right now, in the moment that this sound is reaching your ears, it is drifting through the darkness at roughly 17 kilometers per second, 11 miles per second, about 61,000 kilometers per hour, 38,000 miles per hour. That is the speed it has been moving at more or less since it slipped past Saturn in November of 1980. No engine, no course correction, no change. Just the silent, unbroken coast of a machine that long ago received everything it would ever need from gravity, and now simply travels. In the time it has taken you to listen to this single paragraph, Voyager 1 has moved roughly another 1,500 kilometers further from Earth. Almost 1,000 miles. While you have been breathing in and breathing out, listening calmly, perhaps lying in bed, perhaps with your eyes closed, the spacecraft has slipped another small fraction further into the dark. It does not stop. It does not slow. It does not rest. It has not in any meaningful sense taken a single break in 49 years. So where is it? Right now. As you listen, it is somewhere in the constellation Ophiuchus, the serpent bearer, a wide, faint constellation between Sagittarius and Hercules, hanging in the summer sky of the northern hemisphere. If you go outside on a clear night around the middle of the year and you look toward the south, somewhere up there in the empty space between the stars, that is the direction. Not toward any single star, just outward. Into the soft, dark gap between the shoulders of Ophiuchus and the head of Sagittarius. That is where Voyager 1 is. That is where it is going. The distance is almost impossible to hold in your mind, so let us try anyway. As of the time this video is being made, Voyager 1 is approximately 170 astronomical units from Earth. 1 astronomical unit is the distance from the Earth to the Sun, about 150 million kilometers, about 93 million miles. That is 1 unit. Voyager 1 is 170 of those, lined up end to end, away from you. In kilometers, the number is roughly 25.5 billion. In miles, somewhere close to 16 billion. The numbers stop meaning anything after a certain point. So let me try a smaller picture. Imagine for a moment that the orbit of Neptune were the size of a dinner plate sitting in front of you on a table, just an ordinary dinner plate, roughly 30 centimeters across, about a foot wide. The sun would be a tiny pinprick of light in the center of the plate. Earth would be a microscopic dot, far too small to see, just a centimeter or so out from the middle. Neptune would be at the very rim. The whole thing you grew up calling the solar system, every planet you ever learned about in school, would fit inside the rim of a single dinner plate. Voyager 1, at this scale, would be sitting somewhere on the table just outside the plate, not very far outside. About 6 or 7 centimeters past the rim, a small object, out there, just barely past the edge of the dish, quietly drifting across the wood of the table into the empty space where nothing else has been placed yet. That is where it is. That is what we mean when we say it is out there. It is not far across the kitchen. It is not in the next room. It is just past the rim of the plate, on a table that, as we will soon see, stretches across a room 1,000 times bigger than you can yet imagine. But for now, just hold that image. The plate, the pinprick sun, the tiny edge. The small dot just beyond the rim. That is Voyager 1 on the table of our solar system in this exact moment. Now let us talk about the signal, because here is something almost no one stops to think about. Voyager 1 is so far away now that even light, the fastest thing in the universe, the absolute speed limit of reality itself, takes a long time to make the trip. As of this year, 2026, a radio signal sent from Earth takes more than 23 hours to reach the spacecraft. 23 hours, almost a full day. If you sent a hello right now, traveling at the speed of light, it would not arrive until tomorrow. And the same is true going the other way. Whatever Voyager 1 is whispering back to us today, the signal it is currently sending, the data we will receive tomorrow, was emitted yesterday. By the time it reaches the great radio dishes on Earth, the spacecraft has already moved another 1.5 million kilometers further along. The information arrives late, and from somewhere else, from a position the probe has already left. By the time a packet of data lands on the ground, Voyager 1 is no longer where it was when the data started its trip. This is what it means to communicate with something at the edge of the solar system. There is no real-time conversation. There is no back and forth. There is only the slow exchange of letters across an unimaginable distance, where each letter takes a full day to arrive. The project manager for Voyager at NASA's Jet Propulsion Laboratory, a woman named Susan Dodd, described it this way. She said, if I send a command at 8 in the morning on a Monday and I tell Voyager, good morning, I will not hear Voyager's response until Wednesday morning at about 8. 2 full days, every command, every check-in, every question, 2 days, always. Imagine working with a colleague who only writes back to you every 48 hours. Imagine being a doctor who could only get 1 heartbeat reading from a patient every 2 days. Imagine driving a remote control car that takes a full day to respond to stop. That is what it is like to operate Voyager 1 in 2026. The team sends a command into the dark, and then they wait, and then 2 days later perhaps they find out what happened. Now, in November of this year, this current year, something quietly historic is going to happen. Voyager 1 is going to cross a threshold no human-made object has ever crossed before. Around the middle of the month, on or near November 15, 2026, the spacecraft will reach a distance of approximately 25.9 billion kilometers from Earth, about 16.1 billion miles, and that specific distance is special. That specific distance has a name. It is one light day. A light day is exactly what it sounds like. It is the distance that light travels in 24 hours, not in a year, not in a lifetime, in a single day. Light, the fastest thing in the universe, the standard against which all other speeds are measured, takes 1 full day to cross it. And in November of this year, Voyager 1 will be exactly that far away from us. The first object built by human hands to ever cross such a line. From that moment onward, every command sent to Voyager 1 will take a full day to arrive, and the response, if any, another full day to come back. The round trip becomes 2 days, every time, forever. Or more honestly, for as long as the spacecraft has power to listen. It is a quiet milestone. It will not be on the front page of most newspapers. There will not be parades. Most people will go to work and come home and go to sleep that day and never know it happened. But it is real. For the first time in the history of our species, we will have built a thing that is more than 1 full day of light from us. We have measured distance in light seconds before. The moon is about 1 1/3 light seconds away. We have measured it in light minutes. The sun is 8 1/3 light minutes away. We have measured it in light hours. Pluto, on average, is around 5 1/2. But now, finally, we are about to start using a new unit for a thing we ourselves have made: light days. By the time Voyager 1 eventually falls silent, sometime in the next decade or so, the distance to it will be measured in fractions of a light week. Think about that. A spacecraft far enough away that we measure the distance in how long it takes light to fly there. A spacecraft we have built, with our own hands. Now here is the strange and quietly painful part. While Voyager 1 is approaching this milestone, while it is becoming the most physically distant achievement in the history of our species, it is also slowly dying. Not dramatically. Not in a single sharp failure, just a slow, gentle dimming, a long, patient quieting down. As I mentioned earlier, only two scientific instruments are still operating: the plasma wave subsystem, the magnetometer. Both of them are listening faintly to the texture of interstellar space. The plasma wave subsystem is essentially a pair of long antennas that pick up oscillations in the surrounding plasma, the thin, ionized gas that fills the space between the stars. The magnetometer feels the direction and strength of the local magnetic field. Together, they are giving us the only direct measurements ever made from outside the bubble of our sun's influence. The only ones. There are no others. There is no second source. Voyager 1, and to a lesser extent its sister Voyager 2, are the entirety of human knowledge about what space actually feels like out there. But the power is running out. The 3 radioisotope generators are getting weaker every year. 4 watts lost per year every year. It does not sound like much. But by 2030, by 2035, there will not be enough power left to run even the 2 remaining instruments. By 2036 at most, even the engineering data, the basic vital signs that tell us the spacecraft is still alive, will probably become impossible to transmit. After that, Voyager 1 will keep moving. It will keep coasting. It will keep traveling, but it will be silent. And so the team at JPL has been quietly making peace with that. For decades now, they have been turning things off, one by one, like a hospice nurse making a patient comfortable. Heaters that protect critical components from the deep cold of interstellar space. Backup systems. Cameras. They have not had any working cameras since 1990, when Voyager 1 took its last photograph, the famous pale blue dot, looking back at the Earth from a distance of about 3.7 billion miles. After that, the cameras were switched off to save power for the instruments that still mattered. They have not seen anything since, and in the last few years, there have been some genuinely frightening moments. In late 2023, something began to go wrong. The data coming back from Voyager 1 stopped making sense. The numbers, the readings, the patterns, all of it had become gibberish. A jumbled stream of ones and zeros that the engineers on Earth could not interpret. For 5 months, no one on Earth was sure whether Voyager 1 was still doing science, or whether the spacecraft had effectively gone mad. The engineers worked the problem, slowly, carefully, with the patience of people who knew that every command they sent would take a full day to arrive and another to respond. They diagnosed it eventually. A single chip on the flight data subsystem had quietly failed. A tiny piece of memory, almost half a century old, had finally given up. And so the team rewrote the relevant software, line by careful line, sent it across the gap, asked the spacecraft to rearrange its own brain at a distance of more than 15 billion miles. And somehow, Voyager 1 understood. By the spring of 2024, it was sending back clean science again. There have been other scares. In October of 2024, the spacecraft suddenly switched its main radio transmitter off. The fault protection system, an automated safety mechanism, had decided that something was wrong, and lowered the data rate to conserve power. Then, days later, the transmission stopped entirely. The team eventually realized that the spacecraft had quietly fallen back onto its S-band transmitter, a backup unit that had not been used in any serious way since 1981. The engineers had to learn how to work with a transmitter that most of them were not even alive to have helped design. They got it talking again. By mid-November, the X-band radio was back online, and the data started flowing once more. And between May of 2025 and February of 2026, there was a long, strange silence. The single antenna on Earth that is capable of sending commands to Voyager 1, Deep Space Station 43, in Canberra, Australia, was taken offline for major upgrades. For most of a year, no one on Earth could give Voyager 1 any instructions. The spacecraft kept sending data, faintly, to other antennas that could still listen, but it could not be told anything new. It just had to keep doing what it had been doing the last time anyone spoke to it and wait, patiently, in the cold and the dark, a small, silent machine, waiting for the only voice in the universe that knew its language to come back. This is the strange, tender truth of Voyager 1 in this exact moment. It is the most distant thing we have ever made. It is approaching a milestone no other human creation has ever approached. And it is being held together by a small group of engineers, many of whom are now in their 70s and 80s, who have been speaking to this machine for almost their entire adult lives. They speak its language. They know its quirks. They know which thrusters are clogged. They know which heaters are off. They know that everything on board, as the project manager has said, is now single string, meaning there is no backup left for almost anything. If one critical component fails, that is it. The mission is over. And one day, somewhere in the next decade, it will be over. The plutonium will fade past the point of usefulness. The signal will drop below the noise. The last command will be sent. The last response will be received. And then there will be silence. Voyager 1 will keep moving. It will keep coasting. It will keep drifting outward at 38,000 miles an hour on the same path it has been on since 1980. But we will no longer be in contact with it. We will know roughly where it is because we know where it is going, but we will not hear from it again. It will become a memory, a dot on a chart, a small thing somewhere out there with the gold record on its side drifting forward in silence. So before we go further, let me ask you something. Take a moment with this. Somewhere on Earth, right now, in a small office in Pasadena, California, there is an engineer whose job it is to listen to Voyager 1, to send commands to it, to wait 2 full days for an answer, to keep this tiny machine alive across a distance no living person can truly imagine. What do you think that feels like? To say good morning to something 15 billion miles away, and to know that nothing else in the universe will answer the way it does. Tell me in the comments. I want to know what you imagine when you picture that office, that screen, that quiet 2-day wait. And once you have that picture in your head, I want you to hold it, because we are about to do something almost cruel. We are about to take everything we just said. The 23-hour signal delay, the light day milestone, the 16 billion miles, the most distant thing we have ever made, all of it, and we are about to make it small. Because the truth, the strange and humbling truth that Voyager 1 is about to teach us, is that this immense distance, this distance so vast that even light needs a full day to cross it, is not even the beginning of the journey. The story you have just heard, the long coast through nearly half a century of darkness, ending at a light day from Earth, that is not the end of Voyager 1's journey. That is the part that happens before anything interesting really begins. In the next section, we are going to crack open the comfortable picture of Voyager 1 having reached interstellar space. We are going to look very carefully at what that phrase actually means and does not mean. And we are going to see, for the first time in this story, just how strange and disorienting the real scale of where Voyager 1 is, and where it is going truly is. August 25th, 2012. That is the date you may have heard before. The date that, in the official telling, Voyager 1 entered interstellar space. It is the date in the textbooks, the date in the press releases, the date in the headlines that ran in newspapers all around the world. The day, as one announcement put it, that a human-made object crossed into the space between the stars for the very first time. It is a beautiful date. It is a real date. And it is also, in a way that almost no one stops to think about, deeply misleading. Let me explain what actually happened that day. Because it is one of the most important and most quietly misunderstood moments in the entire story of space exploration. And once you understand it properly, the comfortable picture of Voyager 1, leaving, anything will never quite fit your mind again. The sun, like every star, blows out a thin, ceaseless wind, a stream of charged particles, mostly protons and electrons, pieces of broken atoms, ripped apart by the immense heat of the solar surface and flung outward at hundreds of kilometers per second. This wind, the solar wind, fills the space around the sun. It blows outward in every direction. It pushes against the thin gas between the stars, and in doing so, it carves out a great, invisible bubble around our entire solar system, a bubble of solar particles, a bubble of solar magnetic field, a bubble of, in a deep sense, the sun itself. That bubble has a name. It is called the heliosphere, the sphere of the helios, the Greek word for the sun, and it is enormous, much larger than the orbits of the planets, much larger than the orbit of Pluto. The heliosphere extends, in the direction that Voyager 1 is moving, somewhere around 120 astronomical units from the Sun. That is more than 3 times the distance to Neptune. A vast, invisible bubble of solar wind, holding back the cold gas of the galaxy. At the outer edge of this bubble, there is a boundary. A thin layer where the solar wind, having traveled all that distance from the surface of the Sun, finally slows down, stalls, and stops pushing forward. Beyond that layer, the galaxy takes over. The thin interstellar gas, drifting through the spaces between the stars, presses inward. The two forces meet. And the place where they meet, the surface of contact between solar territory and galactic territory, is called the heliopause, the pause of the Sun, the end of its outward push. On August 25th, 2012, Voyager 1 crossed that boundary. It did not know it at the time. Spacecraft do not know things. They simply measure. But the instruments on board, the same instruments still working today, recorded a sudden and dramatic change. The density of the surrounding plasma increased by a factor of about 40. The direction of the local magnetic field changed. The number of galactic cosmic rays, high-energy particles from outside the solar system, jumped sharply. The number of solar particles dropped almost to zero. Voyager 1 in that moment had crossed a wall, an invisible wall, the wall where the sun's wind ended and the galaxy's wind began. That is what people mean when they say Voyager 1 entered interstellar space in 2012. It crossed the heliopause. It left the bubble of the sun's wind. From that day forward, it has been measuring something no other human-made object has ever measured. The actual texture of the gas and the magnetic field of the galaxy itself in the space between the stars. Now, here is where almost everyone gets it wrong. People hear this. They hear Voyager 1 has entered interstellar space. And in their minds, they translate that into Voyager 1 has left the solar system. But these are not the same thing. They are not even close to the same thing. NASA itself has been very careful over and over to point this out, but the careful version of the story almost never makes it into the headlines. So let me say it clearly, in your ear, right now, in the dark as you listen. Voyager 1 has not left the solar system. It is not on the edge of the solar system. It is not approaching the edge of the solar system. It is, by any honest measure of where our solar system actually ends, still deep inside it. What it has left is the bubble of the sun's wind, the heliosphere, the region of space dominated by particles streaming out of the sun. That is one definition of the solar system's edge, and it is the one some scientists use, but it is not the only one. And it is, in some ways, the least meaningful one, because there is another definition, a simpler, deeper, more honest one. The definition that asks, what holds together a solar system in the first place? And the answer is, of course, gravity, the pull of the sun. By that definition, the solar system is everything that the sun's gravity holds. Every object that orbits the sun, no matter how distant, every comet, every dust grain, every piece of frozen debris drifting along in the long, slow loops of a 500,000-year orbit. By that definition, the solar system does not end at Neptune. It does not end at Pluto. It does not end at the Kuiper Belt. It does not end at the heliopause. It ends much, much farther out, and Voyager 1 has not even begun to approach it. We will get to that next, but before we do, I want to sit for a moment with the numbers, because the numbers, when you really look at them, are almost shocking. Voyager 1 is currently around 170 astronomical units from the Sun. Let us call it 170. The nearest other star to the Sun is Proxima Centauri, a small red dwarf in the Alpha Centauri system. Proxima Centauri is about 270,000 astronomical units away, 270,000 versus 170. Let that math settle in your ear. Voyager 1 has traveled in nearly half a century, about 170 units of distance towards something that is 270,000 units of distance away. Doing the division, the answer is roughly 630 thousandths of a percent, less than 1/10 of 1%. In the most commonly cited form, it is around 0.0027%. 27 thousandths of a percent of the distance to the nearest star. Almost 5 decades of coasting at 38,000 miles an hour, 49 years of unbroken motion, the most distant journey ever taken by anything our species has ever built, and it has covered about 1 part in 38,000 of the distance to the next star. And Proxima Centauri is the closest one, the closest one. Now hold that thought and let me make it worse, because Voyager 1 is not actually heading toward Proxima Centauri. Its trajectory does not point in that direction. It is moving toward a region of sky in the constellation Ophiuchus, into a different part of the galaxy entirely. So even if it kept moving at its current speed forever, even if nothing slowed it down, even if it traveled in a perfectly straight line, it would never reach Proxima Centauri. It is not going there, but even if it were, even if Voyager 1 had been launched on a perfect collision course with the nearest star, at exactly its current speed, the journey would take roughly 73,000 years. 73,000, almost 3 times longer than the entire span of recorded human civilization. Longer than any city we have ever built has stood, longer than any language has been spoken, longer than any continuous tradition we have ever managed. 73 millennia, one way, to the nearest star, and it is not even going there. The galaxy itself, our Milky Way, is somewhere around 100,000 light-years across. 100,000 of those vast distances that light needs a whole year to cross. Voyager 1, in this very moment, is approaching the milestone of being 1 light day away from us. That is the staggering achievement. 1 light day. To put that in perspective, a year has 365 days. The galaxy is 100,000 years across. Multiplying those together, there are roughly 36.5 million light days in a single light year. And there are 100,000 light years across the galaxy. So the galaxy in light days is approximately 3.5 billion light days across. Voyager 1 is about to reach 1. It is at 1. The galaxy is 3.5 billion of them across. Voyager 1 has covered, in nearly 50 years of unbroken motion, about 1 part in 3.5 billion of the width of our home galaxy. I am not telling you this to be cruel. I am not telling you this to make Voyager 1 sound small. I am telling you this because the comfortable picture of a spacecraft leaving a tidy solar system and heading off into a vast but ultimately crossable galaxy is, at every scale, profoundly wrong. The reality is that the spacecraft has barely moved, not because it is slow. By human standards, it is unimaginably fast, but because the distances involved are not human distances. They are not human-shaped. They do not fit inside any image you have ever held in your mind. You have probably seen, somewhere on the internet, a kind of map that tries to show this. A diagram of the solar system, drawn on a scale where every object is shown in something like its real proportional position. And what those diagrams always reveal is the same thing. The planets, even the outer planets, are bunched together in a tiny cluster near the sun. And then there is empty space, vast empty space, stretching outward and outward and outward. And in that vast empty space somewhere, a tiny dot labeled Voyager, and then more empty space. And then far, far beyond, another tiny dot, Proxima Centauri, the nearest star, and then more empty space. The galaxy keeps going. The map keeps going. The picture refuses to fit on any screen. This is the real shape of the place we live in. Not a tidy diagram of 8 planets in 8 neat circles. A vast, mostly empty volume of darkness, with small clusters of warm matter scattered through it at distances so large that even light, the fastest thing in the universe, takes years to make the trip between them. And Voyager 1, the most distant thing we have ever built, is one tiny dot, just barely past the cluster of warm matter we call home, drifting outward through the empty. So when you hear, in 2012, that Voyager 1 has entered interstellar space, what you should hear is this. The spacecraft has crossed a thin boundary in the gas. It has moved from one kind of plasma into another. It has stepped, in some careful technical sense, from solar territory into galactic territory. That is real. That is meaningful. That is, scientifically, an enormous moment, the first time in history that we have a direct measurement of what space is actually like outside the breath of our sun. But it has not left. Not really. Not in any sense that an honest reckoning of the solar system would accept. The sun's gravity still reaches it. The sun's gravity still gently pulls on it. The sun's gravity reaches far, far beyond the heliopause, and Voyager 1 is, by every honest measure, still inside the territory the sun gravitationally rules. There is a remarkable phrase that NASA uses. They say much of interstellar space is actually inside our solar system. Read that again. Much of interstellar space is actually inside our solar system. The space between the stars, the cold and dark region we call interstellar, extends inward, well within the gravitational reach of our own sun. Voyager 1 can be in interstellar space and inside the solar system at the same time. They are not contradictory. They are not the same kind of measurement. Crossing the heliopause is like swimming out past the place where a river meets the sea. Yes, the water around you has changed. The chemistry has shifted. The taste, if you could taste it, would be different. You have, in some real sense, entered the ocean, but you have not crossed the ocean. You have not reached the other shore. You have just barely stepped off the riverbank, and the ocean stretches outward from where you stand in every direction, for distances so vast that the river you came from, looked at from far enough away, becomes invisible. That is where Voyager 1 is, just past the river mouth, with the open ocean ahead of it, stretching in every direction. For what we are about to see is an almost unbearable distance. So before we continue, I want you to sit with one more question, honestly, in your own mind. When you first heard, all those years ago, that Voyager 1 had entered interstellar space, What did you picture in your head? Did it feel like a door closing behind it, as if some final boundary had been crossed? Did it feel like a finish line, the end of a long mission? Or did it feel like a doorway opening, the very beginning of something much longer? Tell me in the comments. There are no wrong answers. I am genuinely curious what image you were carrying, because almost all of us were carrying some version of one or the other, and the truth is so much stranger than either. Because the truth is this: it was not a door closing. It was not even a doorway opening. It was a single, small step across a thin patch of changing gas. And ahead of Voyager 1, stretching outward for something like 1,000 times the distance it has already traveled, lies a region of the solar system that almost no one ever talks about. A region we have never seen, a region we have never visited, a region that no spacecraft in any of our lifetimes will ever reach. That is what we are going to walk into next: the hidden second half of the solar system. The vast, ghostly, almost mythological region that begins where the careful diagrams stop and stretches outward, halfway to the next star. This, finally, is where the journey of Voyager 1 actually begins. If you grew up looking at diagrams of the solar system, you grew up looking at a lie. A friendly, useful, beautiful lie, but a lie nonetheless. The diagrams showed you 8 planets in 8 neat orbits, with maybe a little belt of asteroids tucked between Mars and Jupiter, and perhaps, drawn in faintly at the edge, a Kuiper belt of icy debris beyond Neptune. And then just past that, a clean edge, a clean line, a clean end. Beyond that line, the diagram simply stopped. The page had a border, the poster had a frame, and whatever was past that frame was, by silent agreement, not the solar system anymore. That is the picture you carry in your head. That is the picture I carried in mine. And it is, in the most fundamental way, wrong. Because the solar system does not end where the diagrams end. It does not end at Neptune. It does not end at Pluto. It does not end at the Kuiper belt. It does not even end at the heliopause, where Voyager 1 crossed in 2012. The actual edge of the solar system, the boundary that astronomers, when pressed honestly, will admit is the only one that really matters, lies much, much, much further out than any of those. And it has a name. A strange, almost mythological name, because for most of human history, this region was not known to exist at all. It is called the Oort cloud. The Oort cloud is named after a Dutch astronomer, Jan Oort, who proposed its existence in 1950. He was trying to solve a puzzle. The puzzle was this: there are comets that come into the inner solar system from time to time, comets we have known about for centuries. And some of these comets, the long-period ones, have orbits so vast, so elongated, that they spend most of their time impossibly far from the Sun, tens of thousands of times further than the Earth. They visit once, swing past, and then vanish back outward for tens of thousands or even hundreds of thousands of years. Where, Oort asked, were these comets coming from? Where were they going back to? They could not have formed where they currently live, in the deep cold of the outer dark. They must have been scattered out there at the dawn of the solar system by the gravity of the giant planets, and there must, he reasoned, be a vast reservoir of them. A halo, a shell, a swarm of icy bodies surrounding the sun at a distance so great that the human mind reels trying to hold it. That swarm is the Oort cloud, and here is the first thing you need to know about it. We have never seen it. Not directly, not once. No telescope has ever resolved a single object in it. No spacecraft has ever visited it. No image has ever been taken of it. We know it is there only by inference, by the orbits of the comets that fall inward from it, by the gentle ways in which passing stars seem to disturb something we cannot see, by the mathematics of how a solar system forms. It is the most ghostly, the most theoretical, the most almost mythological part of our own home, and yet it is, by a vast margin, the largest part of our home. Let me give you the numbers. And then let me try, in a small and clumsy way, to make them mean something. The Oort cloud is thought to begin somewhere between 1,000 and 2,000 astronomical units from the Sun. Some estimates put the inner edge slightly further out, around 5,000 units. The honest answer is, we are not entirely sure. Astronomers express it carefully. They say somewhere between. But let us take a middle value. Let us say the inner edge of the Oort cloud is around 2,000 astronomical units from the Sun. Voyager 1 right now is at about 170. That means Voyager 1 has, in nearly 50 years of unbroken coasting, traveled about 1/12 of the way to even the inner edge of the Oort cloud. The inner edge, the beginning of the region. And it is not the inner edge that defines the solar system. It is the outer edge. The outer edge of the Oort cloud is thought to extend to roughly 100,000 astronomical units. Some estimates push it further, to 150,000. Again, the honesty matters. We do not know exactly, but 100,000 is the figure NASA most often cites. 100,000 astronomical units. The Sun's gravity at that distance has finally become so weak that the pull of other nearby stars begins to overtake it. Beyond that, an object is no longer gravitationally bound to our Sun. Beyond that, in the most honest sense, you have left. So look at the ratio. Voyager 1 is at 170 units. The outer edge of the solar system, the real one, the gravitational one, is at 100,000. Voyager 1 has covered, in its entire journey, about 1 part in 600 of the distance to the actual edge, about 0.17%, almost 50 years of coasting. Less than 0.2%. I want to give you a different image, a new picture for your mind, because that earlier image of the dinner plate was true for the inner solar system, but it is wrong for the real solar system, so replace it. Imagine instead a football field, a real one, 100 yards long, end zone to end zone. Place a small marble on one goal line, that is the Sun. A few centimeters away, almost touching the marble, the inner planets, Earth, Mercury, Venus, Mars. So close to the Sun at this scale that they are almost in contact with it. A few centimeters further, Jupiter, Saturn. A handspan further, Uranus and Neptune. By now, you have moved maybe half a meter, less than 2 feet, along the football field. The orbits of all the planets fit easily within a meter of the goal line. The Kuiper belt extends a little further, perhaps another meter or so. By now you are about 3 meters along the field, roughly 10 feet. Pluto and its cousins drifting in slow orbits at the rim of the planetary disk. Voyager 1. Where is Voyager 1 on the football field? At our current scale, it would be at about 6 meters from the goal line, about 20 feet. That is it. 20 feet down a 100-yard football field. That is where Voyager 1 sits in this very moment. Where is the heliopause, where Voyager 1 crossed in 2012? About 4.5 meters from the goal line on this scale, 15 feet. So Voyager 1, having crossed the heliopause, is now slightly past it. A small dot, a few feet beyond the place where the solar wind ends. But where is the inner edge of the Oort cloud? At 2,000 astronomical units. On our football field scale, the inner edge of the Oort cloud is 60 meters down the field, 200 feet, 650 feet, more than half the length of the football field away from the marble at the goal line. Voyager 1 has covered 20 feet. The real edge of the solar system, the place where the Sun's gravity loses to the galaxy, is the opposite goal line, 100 yards away, 300 feet. That is the scale of our home. The neat little cluster of planets that the diagrams show you, the bit you have been imagining as the solar system, is the first foot of the football field. The rest of the field, 99 yards of it, is the Oort cloud, and it is dark, it is sparse. It is cold, it is almost completely empty, but it is ours, it is the Sun's. And it is the thing that Voyager 1, traveling at 38,000 miles an hour, has to cross. How long does that take? Here are the numbers. And I am going to slow down for them. To reach the inner edge of the Oort cloud, around 2,000 astronomical units, at Voyager 1's current speed of roughly 3.5 astronomical units per year, will take approximately 300 years. 300 years. That is the inner edge. That is just the beginning of the cloud. 3 centuries from now, somewhere in the 23rd century, long after every person currently alive has died, long after most of the buildings standing today have crumbled, long after entire languages have shifted and changed beyond recognition. Voyager 1 will at last drift past the first faint scattered objects of the inner Oort cloud, and then it will keep going. To reach the outer edge, around 100,000 astronomical units, will take approximately 30,000 years. 30,000 years. Let that number settle in your ear for a moment, because I do not think any of us, no matter how many times we have heard large numbers, really have a sense for what 30,000 years means. 30,000 years ago on this planet, our species was beginning to paint on the walls of caves. The bison and horses of Lascaux and Chauvet had not yet been drawn. Woolly mammoths still walked across Eurasia and North America. There was no agriculture, no writing, no city, no metal. The most advanced technology in the world was a carefully chipped flint blade, lashed to a wooden shaft. The entire span of human civilization, from the first written word to the device you are listening on right now, fits inside the last 6,000 years. And Voyager 1, from the moment it reaches the inner edge of the Oort cloud, will take 5 times longer than all of that to reach the outer edge. Picture it. 300 years from now, Voyager 1 quietly drifts past its first faint, frozen visitor. Some lump of ancient ice, perhaps a few kilometers across, drifting along on a 500,000-year orbit it has held since the dawn of the solar system. The two of them, the icy body and the small dead spacecraft, pass each other in the dark, separated by perhaps a few 100 million kilometers, neither one ever knowing the other was there. No light from the sun reaches that distance with any meaningful warmth. No instrument on Voyager 1 is awake to notice. It just passes. The first encounter in a region we have only ever known by inference, and then another 3 centuries pass, and another, and another, and the inner Oort cloud thickens sparsely around the spacecraft. The frozen comets here are mostly arranged in a thick, flattened disk, a torus like a donut, roughly aligned with the plane of the planets. This is sometimes called the Hills cloud, after the astronomer Jack Hills, who proposed it. It is the dense inner part of the larger structure. Even here, the density is so low that an object the size of Voyager 1 could drift through for thousands of years, and never come within 1,000,000 kilometers of another body. The cloud is enormous, but its contents are spread across so much volume that, in any practical sense, it is empty. Beyond the Hills cloud, further out, the geometry changes. The disk shape opens out into a sphere. The outer Oort cloud surrounds the sun in every direction, above and below the plane of the planets, a roughly spherical shell of icy debris hanging in the cold. The objects out there are bound to the sun, but only weakly. The pull of nearby stars can shift them. The slow gravitational tide of the galaxy itself can nudge them. Every once in a great while, one of these objects gets tugged just slightly, just enough, to begin a long, slow fall back toward the sun. Hundreds of thousands of years later, it arrives in the inner solar system as a long-period comet, glowing faintly in the warmth, before swinging out again on a vast new orbit. We see these comets. We have named some of them. We have measured their tails. But we have never seen where they came from. Voyager 1, in around 30,000 years from now, will drift past the outermost of these objects, the last frozen scrap of comet, the last gravitational whisper of our sun. And then, only then, in any meaningful sense of the word, it will have left. Now, here is a thought that I want to give you, gently, because it is one of the most strange and humbling thoughts in the whole story of our cosmic neighborhood. Roughly half of the objects in the Oort cloud may not even have originated in our solar system. When the sun was very young, it was not alone. Stars do not form in isolation. They form in clusters. Great nurseries of newborn stars, packed close together, sharing the same enormous cloud of gas and dust. The sun was born into such a cluster, with hundreds or thousands of stellar siblings, all crowded into a region perhaps a few light years across. And in that crowded infancy, as each young star sprayed out its own little halo of icy debris, the stars stole from each other. They tugged. They lifted. They exchanged comets like children passing pebbles in a playground. By the time the cluster eventually dissolved, and the sun drifted off on its own, it took with it a halo of icy bodies, some of which had been born around other stars entirely. Stars that, 4.5 billion years later, are now scattered all across the galaxy, each one carrying away its own piece of the sun. So if Voyager 1 could see, in the 30th millennium of its journey, what it was actually drifting past, some of those frozen objects would be sisters from the lost cluster, cousins of the sun, pieces of other suns, captured at the dawn of everything, and held in the sun's gentle grip for 4.5 billion years. That is the place Voyager 1 is going. That is the place no diagram in your schoolbook ever showed you. That is the real edge of our home, and it does not stop until 30,000 years from now. Take a moment with that. Take a moment to feel how the picture in your head has just been pulled outward. Because the comfortable, tidy little solar system you were taught about, the one that ends at Pluto or Neptune or maybe at the Kuiper Belt, is not real. It is a useful diagram for school. But the real solar system, the one we actually live in, is 1,000 times bigger than that, maybe more. And almost all of it, the overwhelming, vast, ghostly majority of it, is dark, cold, almost empty, and populated only by drifting fragments of frozen water and methane and ammonia, looping in slow orbits that no human being has ever seen, and no human being ever will see. This is the place Voyager 1 is heading into. This is the place the spacecraft has not yet entered. This is the place the spacecraft will not reach for 3 centuries. This is the place the spacecraft will not finish crossing for 30,000 years. And when I say the spacecraft will not finish crossing, I want you to hear something carefully. By then, Voyager 1 will have been silent for nearly 30,000 years. The plutonium will have decayed past usefulness sometime in the next decade. The signal will have faded into noise. The cameras, the heaters, the radios, the antennas, all of it will have been dark for by then, almost 300 centuries. The spacecraft will keep moving. It will keep drifting. It will keep coasting on the same trajectory at the same speed it has been holding since 1980. But there will be no one listening. There will be no one watching. There will be no one in contact with it. And by then, on our small blue world, almost everything you can name will be gone. Every language we speak today will have evolved into something unrecognizable, if it survives at all. Every country whose borders you can picture will have changed beyond knowing. Every city will be a ruin, or a different city built on top of an older one, or a shape pressed into the earth that some future archaeologist puzzles over. The people you love, the people who love you, the streets where you live, every word you have ever read. All of it will be gone, or transformed, or remembered only as the most ancient of histories, the way we now think of the cave paintings of Lascaux. And Voyager 1 will still be moving, still inside the solar system, still drifting through the outer Oort cloud, still carrying its small golden disk with a recording of a kiss and a heartbeat and Chuck Berry playing the guitar. So before we continue, let me ask you something. Does it change how you think of the Earth, knowing that the sun's reach extends 1,000 times further than the orbits you learned in school? That the planets, all of them together, are only the first foot of a football field. That almost everything that belongs to our sun, 99% of the volume of our home, is a region you have never seen pictured. Take a moment, sit with it, and tell me in the comments how the picture in your head feels now compared to the picture you had at the start of this video. I want to know. Because once you have felt the weight of that, once you have truly let the size of the real solar system settle into your mind, we are ready to step further still. Because somewhere out there, far beyond the outermost comet of the outer Oort cloud, somewhere in the gulf between the sun and the next star, Voyager 1 is going to start passing things that no longer belong to our sun at all. Other stars. Drifting in their own orbits around the galactic center, moving on their own paths. Some of them, slowly, silently, are coming closer. And one of them, a small red dwarf in the constellation Camelopardalis, is currently moving toward Voyager 1 faster than Voyager 1 is moving toward it. In about 40,000 years they will meet, not closely, not warmly, but they will pass within sight of each other, and that finally is when Voyager 1 begins what we might honestly call its second journey. That is where we are going next, 40,000 years. I want you to start by holding that number, not as a statistic, not as a piece of information, as a length of time, 40,000 years, roughly 6 times longer than every chapter of recorded human history added together. Roughly 8 times longer than the oldest continuously built city on Earth has stood. Roughly 13 times longer than the pyramids at Giza have been standing in the desert. The amount of time it would take, if you began counting 1 second at a time, with no breaks for sleeping or eating, to count to 1,261,000,000. That is how long it will take Voyager 1 to reach its first stellar encounter. Because somewhere out there in the direction the spacecraft is moving, in a constellation called Camelopardalis, the giraffe in the northern sky between Cassiopeia and the pole star, there is a faint, dim red dwarf. Most people, looking up at a clear night sky, would never notice it. It is too dim. Your eyes cannot see it. You need a telescope to find it at all. Even with a telescope, it is a small, ordinary thing. The kind of star astronomers catalog and move on from. Nobody writes love poems about it. Nobody points it out to children. It does not have a beautiful classical name like Sirius or Vega or Betelgeuse. It has a catalog name, a label, a piece of bureaucratic astronomy. It is called Gliese 445. In older catalogs it goes by another name, AC plus 79 3888. But Gliese 445 is the name most often used now. A small red dwarf about a third of the mass of our sun. Cool, dim, old, almost completely unremarkable. The kind of star that, in our galaxy of 200 billion stars, would never even be noticed if not for one strange and quietly extraordinary fact. It is moving, and it is moving toward us. Stars, you may have heard, are not fixed. The night sky is not a stage with the actors permanently in their positions. Every star you have ever seen is moving, drifting. Each one carried along on its own orbit around the center of the Milky Way, traveling through space at hundreds of kilometers per second, in patterns that, over thousands and millions of years, gently rearrange the sky. The constellations we know, Orion's Belt, the Big Dipper, the Great Square of Pegasus, are illusions of this moment. Snapshots, frozen pictures of stars that happen, right now, in this particular 10,000-year window to look as if they belong together. 10,000 years from now, the Big Dipper will not be a dipper anymore. Its stars will have drifted enough to break the shape. 40,000 years from now, the night sky will look noticeably, significantly, recognizably different. And in that drifting, in that slow tide of motion, Gliese 445 is coming toward our sun. Right now, today, it sits about 17.5 light-years away. That is a very long way, 50 times further than the nearest star, Proxima Centauri. But Gliese 445 is not staying put. It is moving in our general direction, at a respectable speed, and the strange truth is this. By the time Voyager 1 reaches the encounter point, in roughly 40,000 years, Gliese 445 will have closed a great deal of that distance. It will have moved closer. Voyager 1 will have moved outward, and the two of them will meet, not at the spot where the star currently sits, but somewhere in between. This is a thing almost nobody mentions when they tell this story. Gliese 445 is, in a very real sense, moving toward Voyager 1 faster than Voyager 1 is moving toward it. NASA itself, in describing this encounter, has noted this. The star is doing more of the work. Voyager 1 is, in some ways, just waiting. And at the moment of closest approach, in roughly the year 42,272 by our current calendar, by some calculations 44,000 years from now, the two will pass each other at a distance of approximately 1.6 light-years. Some estimates say 1.7. Either way, a fraction more, a fraction less, the answer is roughly the same, a little over a light-year and a half. Closer than Proxima Centauri is to the Sun today. By the standards of interstellar space, an extremely close pass. I want to put that in some kind of perspective. Right now, the nearest star to our Sun is Proxima Centauri, at about 4.2 light-years. Voyager 1, 40,000 years from now, will be within 1.6 light-years of Gliese 445. So the spacecraft will be closer to that star than any other star is currently to our Sun. At that moment, 40,000 years from now, the closest sun to Voyager 1 will not be our Sun anymore. It will be Gliese 445. That is the strange, almost ceremonial fact of the encounter. After 40,000 years of drifting through the deep dark of crossing the inner Oort cloud and the Hills cloud, and the outer spherical halo of finally at last leaving every gravitational tie to our home Voyager 1 will, for the first and only time in its history, be closer to another star than to the Sun that built it. Some new red dwarf in a constellation called the Giraffe will inherit it, briefly, gravitationally, as the dominant star in its sky. Not that there will be any sky. Not that there will be anything to see. Voyager 1 will be long dead by then, long dark, long silent. The plutonium will have been gone for 39,090 years, give or take. The instruments will have been off for almost as long. The metal of the antenna will have been gently corroded by tens of thousands of years of cosmic rays. The gold of the record, slightly tarnished. Bolts loosened, perhaps, by the slow thermal cycling of 40 millennia in the cold. The spacecraft will be a ghost. A perfectly preserved ghost, almost certainly still recognizable, still mostly intact but utterly inert. No light coming from it, no signal, no sense of itself. And it will drift past Gliese 445 at a distance of about 1.5 light-years, which is still vast on a human scale but small on a galactic one. And neither one will know the other was there. Will the star have planets? Honestly, we do not know. Red dwarfs often do. Some of them have several. Some of them have rocky worlds in their habitable zones, where liquid water could exist on the surface. Gliese 445 has not been studied in great detail because, frankly, it is small and dim and far away, and there are more interesting targets for the limited telescope time astronomers have to work with. But it is entirely possible that, when Voyager 1 drifts past, there will be planets in orbit there. Frozen ones, maybe rocky ones, maybe a small wet one with something living on it. We have no way of knowing. If there are planets, the geometry is wrong for an encounter. 1.6 light-years is far too distant to pass through a planetary system. Voyager 1 will sail past, well outside the gravitational reach of any planet. It will not enter the star's neighborhood, not really. It will not be captured. It will not collide. It will not slow down. The red dwarf's gravity will tug on it faintly, but a 38,000-mile-an-hour passing object, at a distance of 1.5 light years, is far too fast and far too far to be held. The encounter will be like two boats passing each other on a vast lake at night, neither one seeing the other's lights, the only evidence of the meeting being a faint, faint ripple in the wake. But still, there it is, Voyager 1's first true stellar encounter. A small red star, sitting where Voyager 1 was launched, light years away from the launch pad in Florida, ages and ages from any human who can remember why we sent it. And then it keeps going. Because, and this is the part that always quietly amazes me, Gliese 445 is not the only encounter. It is just the first. Voyager 1 will, in the long course of its drift through the galaxy, brush past many stars. In about 56,000 years, Voyager 1 will finally exit the outermost edge of the Oort cloud entirely. The last frozen fragment, the last gravitational scrap of our solar system, will fall behind. From that point on, it will be in true interstellar space. Not the careful technical definition from 2012. The honest definition. The kind where you have left, in every meaningful sense, the gravitational territory of the sun, and you are simply a piece of debris drifting through the galaxy, orbiting the center of the Milky Way along with everything else. In about 303,000 years, Voyager 1 will pass another star, a small main sequence star called TYC 3135-52-1. It is a more obscure name than Gliese 445, a catalog identifier from a star survey, the sort of name astronomers use for the millions of small stars that nobody pays much attention to. The closest approach to TYC 3135 will be about 0.965 light-years. Slightly less than a light-year, closer than the encounter with Gliese 445. A near miss by the standards of interstellar travel, although still impossibly far by any human measure. In around 570,000 years, Voyager 1 will brush past two more stars. They are called GJ 686 and GJ 678, two more catalog names, two more unremarkable stars, two more silent encounters in the long, dark drift. And then, in around 5.7 million years, something larger will change. Voyager 1 will exit a region of space astronomers called the local bubble. The local bubble. I want to take a moment with that name, because it is a curious one, and it points to something most people have never heard of about the place we live. Our sun, and our entire solar system, is currently drifting through an enormous cavity in the interstellar gas of the galaxy. A roughly bubble-shaped region of relatively empty space, about 300 light-years across, with much thinner gas inside than outside. It is thought to have been carved out, millions of years ago, by the explosive deaths of nearby massive stars. A series of supernovae, scattered across what is now this region of the galaxy, blew the gas outward and left a great cavity behind. The sun, on its own quiet orbit around the galactic center, happens to be drifting through this cavity right now. The local bubble, Voyager 1, for the next 5.5 million years, will continue to drift inside this bubble. The space around it will be a little warmer, a little thinner, a little stranger than the average of the galaxy. And then, around the 6 million year mark, it will finally exit. It will pass into the denser, colder, more typical gas of the surrounding galaxy. And from there, the journey gets harder to predict. This is something honest that I want to share with you carefully. The further out in time we look, the murkier the picture gets. The motions of stars and dust clouds in the galaxy are not perfectly known. Small interactions over millions of years can change a trajectory in subtle ways. There may be wandering, starless planets out there, rogue worlds drifting through interstellar space without any sun, ejected from their birth systems long ago. Voyager 1 could pass close to one. The gravity could, very slightly, deflect its path. It could pass through dust clouds, and the friction of those clouds, however small, could slow it down over millions of years. We do not know exactly. We can only make educated guesses, and the further out we project, the looser those guesses become. But within the limits of what we can predict, here is the picture. Voyager 1, after exiting the local bubble, drifts onward into the deeper galaxy. More stars come and go in its sky. Most encounters will be at distances of many light years. Some will be closer, perhaps a light year, perhaps a fraction of one. Statistically, over hundreds of millions of years, a spacecraft drifting through the galaxy will pass within a few light years of dozens, perhaps hundreds of stars. Each encounter a long, silent moment. Each star a possible alternate sun for a brief instant. Each meeting completely unwitnessed by anyone or anything that knows what it is looking at. And here is the strange and beautiful truth about all of this. Astronomers have estimated in a careful paper looking at the future stellar encounters of various spacecraft on escape trajectories from the solar system, the timescale on which Voyager 1 might actually collide with a star. Not pass near, not have a close encounter, actually collide, strike a stellar surface. The number they came up with is something on the order of 10 to the 20th power years, one followed by 20 zeros. 100 quintillion years. For comparison, the current age of the universe is about 13.8 billion years. That is 1.38 times 10 to the 10th power. The expected collision time for Voyager 1 with a star is about 10 billion times longer than the universe is currently old. Stop and breathe with that. The universe, the entire observable cosmos, the totality of all space and time we have ever measured, has existed for less than 14 billion years. And the expected time for Voyager 1 to crash into a star is around 10 billion times longer than that. The likelihood, in any time frame remotely human, is essentially zero. The likelihood, in any time frame remotely cosmological, is also essentially zero. By the time anything serious has had a chance to happen to Voyager 1, the universe itself will be unrecognizable. The stars currently burning will be long dead. New stars may or may not still be forming. The galaxies we know may have evaporated. The cosmos itself may have entered phases of its life that no current physics can describe with confidence. And Voyager 1, on a long enough horizon, may simply keep drifting. The space is mostly empty. The encounters are mostly distant. The trajectory is, by every honest estimate, almost permanent. The spacecraft, this small, fragile machine built by humans in a clean room in Pasadena in 1977, may very well be one of the longest surviving artifacts of our entire civilization. Not because it was built well, although it was. Not because it carries some special protection. It does not. But simply because space is enormous and mostly empty, and there is almost nothing out there to break it. I want to ask you something, and I want you to take a moment with this one. Because I think it sits at the heart of what we are doing here tonight. If a civilization, 40,000 years from now somewhere in the planets of Gliese 445, happened to detect a small, ancient drifting object passing through their solar system, and they retrieved it, and they understood the symbolic instructions on the cover of the small disc on its side, and they figured out how to play it, and they heard our music and our greetings and a woman's heartbeat, and a baby's first cry and Chuck Berry singing, "Johnny Be Good." What is the one thing you would want them to understand about us? Not what they should know, not what some official committee should send. What you personally would want them to know. Take a moment. Tell me in the comments. I am genuinely curious what each of you would say. Because once you have your answer in your head, you are ready for the strangest part of this entire story. The part where we stop asking how far Voyager 1 can travel and start asking something stranger and lonelier and far more humbling. What if it never stops? What if the small drifting machine outlives the sun, outlives the earth, outlives every star you can see in the night sky, every person you have ever loved, every word that has ever been spoken in any human language. That is where we are going next, to the deep, deep future, where Voyager 1, long after the last lullaby of our species has been forgotten, will still be moving. 4 billion years. That is the next number we have to hold. 4 billion. Not 40,000, not 300,000, not 5 million. 4 billion years from now. Roughly the age of the Earth itself, projected forward instead of backward. In about 4 to 5 billion years from now, our Sun will run out of hydrogen at its core. The fusion that has powered it for the last 4.5 billion years, the slow burn that has heated our planet and grown our forests, and warmed our skin every single morning of every single day of our entire species' existence, will finally come to an end. The core will collapse inward while the outer layers begin to expand. The Sun will swell. It will turn red. It will become what astronomers call a red giant, ballooning outward until it engulfs Mercury, then Venus, and then perhaps Earth itself. Long before that happens, of course, Earth will already be uninhabitable. The Sun does not need to die to kill the Earth. Long before the red giant phase, simply by growing slightly brighter each billion years, as all main sequence stars do, the Sun will boil away our oceans, strip away our atmosphere, and turn our blue world into something resembling a cooler Venus. Most estimates put the end of complex life on Earth at around 1 billion years from now, perhaps 2. By the time the Sun actually begins to expand into a red giant, the Earth has been dead for a long time. A dry, lifeless rock, baked in the slowly intensifying glare of its parent star. And then the Sun swells. And depending on the exact details, depending on how much mass it sheds as it dies, the Earth may or may not be engulfed. Some calculations suggest the Earth's orbit moves outward, just enough, as the Sun loses mass to escape direct contact. Other calculations suggest the Earth spirals in, slowed by the thin gas of the expanding solar atmosphere, and is finally swallowed. Either way, it does not matter much. The result is the same. The planet is unrecognizable. The continents are gone. The oceans are vapor. The atmosphere is stripped. Every fossil that has ever been preserved, every layer of sediment, every cave painting, and every buried city and every coral reef, all of it baked, melted, scattered, or absorbed. That is the end of Earth. And Voyager 1. Where is Voyager 1 during all of this? Voyager 1 is fine. Voyager 1 is by then far away, trillions of kilometers away. So far that the explosion of the Sun, the most violent thing to ever happen in our solar system's history, is, from Voyager 1's perspective, simply a distant brightening of one particular star in its sky. The red giant phase produces no shockwave that could reach the spacecraft. The Sun does not go supernova. It is too small for that. It will simply puff out its outer layers, gently, over the course of millions of years, into a beautiful expanding shell of glowing gas called a planetary nebula. And then the core, the small dense leftover, will settle into what is called a white dwarf. A slowly cooling ember of carbon and oxygen, about the size of the Earth but as massive as the Sun, glowing faintly, then more faintly, then fading toward darkness over the long, long ages. And Voyager 1, at no point during any of this, is in danger. Because by the time the Sun begins to die, Voyager 1 has been gone for billions of years. It long ago left every gravitational tie. It long ago crossed the Oort cloud. It long ago drifted past Gliese 445 and TYC 3135, and the GJ stars, and out of the local bubble, and onward into the deep galaxy. The Sun's death is a distant event. A piece of news that, if there were any way to bring it to Voyager 1's attention, would barely register on its instruments if its instruments still existed. This is the moment in the story I find most strange, most beautiful, most quietly humbling. Because we have spent the entire night talking about Voyager 1 as something we built, something we sent, something we own, and I want you to feel slowly the inversion. Because at this point in the deep future, in the long horizon of cosmic time, the relationship reverses. Voyager 1 is no longer ours. It is just a small object drifting in the galaxy, like billions of other small drifting objects, except for one quiet difference. It is the only one of those small drifting objects that knows it came from somewhere. The sun will be gone. The earth will be gone. We will be gone, almost certainly, or transformed beyond recognition into something our current selves could not imagine. The languages will be gone. The cities will be gone. The species, in any form we would recognize, will be gone. Everything that built Voyager 1, everything that named it, everything that put a gold record on its side and dreamed of who might find it, will have ended. And Voyager 1 will still be moving, still drifting at 38,000 miles an hour, still carrying the gold record, still bearing a small etched message from a forgotten president of a forgotten country, on a forgotten world of a forgotten species, still bearing a recording of a young woman's heartbeat from one summer afternoon in 1977, still, somehow, intact. How long does this continue? How long, really, does Voyager 1 last? Here is where the numbers stop being numbers and start being almost a kind of poetry. Our entire solar system and the sun are on a journey of their own. Like every star in the galaxy, the sun is in orbit around the center of the Milky Way. A long, slow, vast orbit. The radius of that orbit is roughly 26,000 light years. The speed of that orbit is roughly 220 kilometers per second. The time it takes to complete one full lap, one full circuit around the galactic center, is something astronomers sometimes call a galactic year. A galactic year is approximately 225 to 250 million years. Voyager 1, drifting outward from the sun, is also in an orbit around the center of the galaxy. Its orbit will not be identical to the sun's. It will be slightly different, a slightly different inclination, a slightly different speed, a slightly different radius. But the period, the time to complete one lap, will be roughly similar. Voyager 1 will, in some sense, complete one orbit around the Milky Way every 250 million years. Read that again. 250 million years for a single orbit. The last time Voyager 1, on its current trajectory, was at the position it will be in 250 million years, the dinosaurs had not yet evolved. The Permian extinction had just wiped out 90% of all species on Earth. The continents were still partly assembled in a single supercontinent called Pangaea. That is one orbit. 1. Voyager 1 will almost certainly complete many of them. How many? Honestly, here the predictions blur. The honest answer is that nobody knows. Stars get rearranged. Galaxies collide. The orbits of objects in galaxies are not perfectly predictable over billions of years. In about 4 billion years, by the way, something extraordinary will happen to the Milky Way. The neighboring Andromeda galaxy, currently 2.5 million light-years away, is falling toward us. At about 100 kilometers per second, in about 4 billion years, the two galaxies will merge. They will spiral around each other, tearing each other apart and weaving back together, until eventually they form a single, larger, blended galaxy, sometimes nicknamed Mokomeda. And here is the thing that surprises most people. During that merger, almost no stars will actually collide with each other. The galaxies are mostly empty space. Even when two galaxies pass through each other, the stars themselves are so far apart that direct collisions are vanishingly rare. The stars get rearranged. The orbits get disturbed. The shape of the new galaxy is utterly different from either parent, but the individual stars, by and large, drift through unharmed. Voyager 1, during this merger, almost certainly drifts through unharmed too. Its trajectory might be perturbed. Its galactic orbit might be reshaped. It might be flung onto a new path, looping out into the halo of the new galaxy or settling into a different region. But the spacecraft itself, in all likelihood, is not destroyed. It is just rearranged. A small fragment of debris in a rearranged sky. What actually destroys a spacecraft drifting through interstellar space? This is a real question, and it has a real, if somewhat surprising, answer. The main thing that erodes Voyager 1 over the long ages is not collision with stars, not collision with planets, not collision with comets, not even really collision with significant pieces of dust. It is the slow, gentle, almost ceremonial bombardment of micrometeorites. Tiny grains of rock and ice and metal drifting through interstellar space, pinging against the spacecraft at relative speeds of tens of kilometers per second. Each impact, individually, is almost nothing. A single grain of dust hitting the gold record at 20 kilometers per second might leave a tiny crater. Microscopic, almost invisible, but across millions of years those impacts add up. Cosmic rays do their work too. High-energy particles from supernovae and active galactic nuclei slamming into the spacecraft constantly, slowly damaging its materials at the atomic level. The aluminum corrodes very slowly. The wiring degrades. The electronics, long dead, slowly lose any structural integrity. The plutonium itself, the fuel that once warmed the generators, decays away over half-lives of 87 years each, until eventually the radioactive heart of the spacecraft is just an inert lump of lead, the stable end product of the decay chain. But the body of the spacecraft, the metal, the disk, the shape, that in the cold and the vacuum is remarkably hardy. Things in space do not rust, they do not biodegrade, there are no microbes to break them down, there is no oxygen to oxidize them. There is no weather, there is no rain, there is no sun in any practical sense to fade them. They just sit there in the cold and the dark, slowly, slowly, slowly being worn down by the gentlest of cosmic erosions. Estimates of how long Voyager 1 could remain recognizable in the deep vacuum of interstellar space run into the billions of years. Some calculations push them higher, tens of billions, hundreds of billions. The honest answer is that nobody really knows, because we have never observed an artificial object in interstellar space for that long. We can only model, we can only guess. But the modeling and guessing suggest something almost difficult to accept. Voyager 1 could, very plausibly, survive for longer than the current age of the universe. It could outlive the sun by billions of years. It could outlive the death of the last stars, which astronomers estimate will happen something like 100 trillion years from now, when the universe has finally exhausted its supply of hydrogen and the last red dwarfs have winked out. It could, in some scenarios, even outlive the era of galaxies themselves, the era of star formation, the era of light. In the very deep future, hundreds of trillions of years from now, the universe will be a dark place, full of cold remnants. Black dwarfs that used to be white dwarfs, black holes, neutron stars, the leftovers of light, and drifting silently through that darkness possibly still Voyager 1, and on its side still bolted in place the gold record. Now the gold record. This is the thing I want to spend a moment on, because it deserves the moment. The golden record was designed to last. Carl Sagan and his team, knowing that whatever they put on the spacecraft was going to be there for an extraordinarily long time, made specific choices about the materials. The record itself is copper. The plating is gold. The protective jacket is aluminum. These materials were chosen because, in the cold vacuum of space, they do not corrode in any meaningful way. They do not break down. They simply sit there. The conservative estimate, the one most often quoted, is that the gold record could remain readable for approximately 1 billion years. 1 billion. That is, again, a length of time so large that the human imagination cannot really hold it. 1 billion years ago, on Earth, Complex multicellular life had only just begun to evolve. Animals did not yet exist. Plants did not yet exist on land. The continents had different shapes. The oceans had different chemistries. 1 billion years is a piece of time long enough to grow the entire ladder of complex life from scratch. And the record, by conservative estimate, could last that long. By less conservative estimates, by the calculations that take into account just how empty and gentle interstellar space really is, the record could last several billion years. Some estimates push it longer. Some, considerably longer. Which means in plain language this. The gold record on the side of Voyager 1 is, by every reasonable measure, the longest-lived single object that our species has ever manufactured. It will outlive every cathedral, every statue, every monument, every pyramid, every nuclear waste storage facility. Every recording, every book, every photograph, every server, every hard drive, every fiber optic cable. It will outlive them by orders of magnitude, by factors of thousands, by factors of millions in the long run, long after the last book on Earth has crumbled to dust. Long after the last carved stone has been worn smooth by wind. Long after the continents themselves have rearranged into new shapes, and the species that built Voyager 1 has either evolved into something unrecognizable or gone extinct entirely. The gold record on the side of a small 10-sided spacecraft, drifting in the dark, will still be carrying a recording of birdsong and Bach, and a woman thinking about love in a hospital room in 1977. I want you to sit with that for a moment. Because I do not think most people realize this. We were not just building a spacecraft. We were not just sending a science mission to Jupiter and Saturn. We were not just achieving an engineering triumph. By the strange, accidental physics of where the spacecraft was going and what it was made of, we were building, without quite meaning to, the longest-lasting monument our civilization will ever create. A small disk, 12 inches across, bolted to the side of a fragile machine. Drifting forever through the galaxy, that is the legacy, that is what we made. I want to ask you something, and I want you to sit with it honestly. Does it comfort you, or does it disturb you, to know that the longest surviving object made by human hands will most likely be a small gold record full of birdsong, and Beethoven and a kiss, and a heartbeat? Does it feel like a beautiful thing or a sad thing or both at once? There is no right answer here. I am not asking you to defend any view. I just want to know how it sits in your chest as you listen to this in the dark. Tell me in the comments. I want to know. Because once you have that feeling in your body, once you have really let it settle, we are ready to confront the strangest and most quietly important truth of this entire video. The truth that has been creeping up on us all along. The question we have been asking, the question this entire long evening has been built around, the question of how far Voyager 1 can travel, was never really the question. Not in any honest sense. Because the answer, the real answer, is something stranger than a distance. That is where we are going for our final landing, to the place where the question itself dissolves. And we have to ask instead something much harder and much smaller and much closer to home. So here we are, at the end. Let me take you back, all the way back, to the very first sentence I spoke to you tonight, the image I asked you to hold in your head and then promised to dismantle, the familiar picture. A small spacecraft, drifting at the edge of the solar system, winding down its mission, having finally, gracefully, left. And now look at what that image has become. Look at how much larger the world has grown around it in the last 90 minutes or so. We started with a dinner plate. We ended with a galaxy. We started with one moment in 1977 in a clean room in Pasadena. We ended trillions of years from now in the long dark after the last stars have died. We started with a tidy diagram of 8 planets, and we ended with the strange truth that the place we call home extends 1,000 times further than any of those diagrams ever showed. We started with the phrase interstellar space, used confidently, as though it meant something simple. And we ended understanding that it means almost nothing of what we thought it meant. Look at the journey we have taken, from Cape Canaveral, past Jupiter, past Saturn, past Titan, whose haze flung the spacecraft up out of the plane of the planets forever. Across nearly 50 years of unbroken silent coasting, past the heliopause, into the gas between the stars, toward the milestone this November, where for the first time in our species' history, a thing we have built will be more than a full day of light from us. And then, onward. 300 years to the inner edge of the Oort cloud, 30,000 to its outer rim, 40,000 to Gliese 445, 300,000 to a smaller star, 500,000 more to the next, 6 million to leave the local bubble, 250 million for a single lap around the center of the galaxy, billions of years for the death of the Sun and the merger with Andromeda, trillions of years before the last stars wink out, and in the very deep future, longer than any current language has a comfortable word for the slow micrometeoritic erosion of a small 10-sided spacecraft drifting through a darkening universe, carrying on its side a small gold disk on which somewhere in its grooves you can still hear faintly a woman thinking about love. That is the journey, that is the shape of it, that is what we have followed tonight. So now, finally, I want to come back to the question we started with. The question this whole long evening has been built around. How far can Voyager 1 travel? And I want to tell you something honest. I do not think the question has an answer. Not really. Not in the way the question is normally meant. When you ask how far can it travel, you are imagining that there is somewhere a finish line. Some point at which the spacecraft stops, some moment at which the journey ends, some final, definite distance that you can put on a chart and say, that is how far Voyager 1 went. But that is not how this works. That has never been how this works. Voyager 1 does not stop. There is nothing to stop it. Space, in any practical sense, has no friction. There is no air to slow it. There is no surface to land on. There is no destination it is heading toward. There is just the long, slow, eternal coast. The same direction, the same speed, the same trajectory it has held since 1980. Forever, or as close to forever as anything in the universe gets. The spacecraft will not run out of road. It runs out of us. That is the truth. The mission of Voyager 1 will end sometime in the next decade, not because the spacecraft has stopped, but because we have stopped listening. The plutonium will fade. The signal will drop below the noise. The last command will be sent. The last response will be received. And then we will simply stop being able to hear it. And the spacecraft, which from its own perspective has changed nothing about its situation, will continue exactly as it has been continuing, moving at 38,000 miles per hour, in the same direction, at the same speed. It just stops being something we can know about. This is the inversion at the heart of the question. We have been asking, how far can Voyager 1 go? But that is not the right question. The right question, the honest question, the question that the universe actually answers is this: how far can we follow Voyager 1? And the answer to that question is, not very far at all. We will lose the signal in about a decade. We will lose the ability to predict its position with confidence somewhere in the next few 100,000 years. After that, the spacecraft is genuinely gone, not because it has stopped, because it has continued beyond our ability to keep watching. The mission ends when we end, not when it ends. And so, in some quiet and almost painful sense, the real story of how far Voyager 1 can travel is the story of how short our reach is. Not how long the spacecraft's journey is, how short our company on it is. We sent it. We made it. We named it. We taught it everything it knows. We bolted a record to its side that says, this is where we came from, and this is what we sounded like, and this is what we wanted to be remembered for. And then we watched it go. and we will keep watching faithfully for a little while longer, and then we will stop, and it will keep going. That is the strange truth. We are not the ones taking the journey. Voyager 1 is. We are the ones who scent it and stand on the shore and watch it sail past the horizon. And the horizon, in this case, is not the edge of the world. It is just the limit of how far our eyes can see. So if the question is, how far can Voyager 1 travel, the most honest answer is, further than we can ever know, further than we can ever follow, further than our species in any form is likely to last, out beyond the death of the sun, out beyond the death of the earth, out beyond the night sky we currently know, with constellations that will have long since been rearranged into shapes no one alive today could recognize, out into a galaxy that has merged with its neighbor, out into a cosmos that has, by then, entered phases we cannot even properly describe. And inside that long, long drift, somewhere, this small thing that we made. I want to address you directly now because I have been talking to you all night and I want to make sure you can hear me as I say this. You are sitting somewhere, perhaps in bed, perhaps in a quiet room, perhaps with your eyes closed, perhaps in the dark, and you are a small conscious creature on a small wet world in a corner of a galaxy of 200 billion stars in one universe among who knows how many, listening to the story of a small machine your species built that will outlast almost everything you have ever known, the people you love, the streets you live on, the language you speak, the species you belong to, the planet you stand on, the sun whose light has warmed every morning of your entire life, all of it outlived by a small gold disk bolted to the side of a small 10-sided spacecraft drifting in the dark. I do not want you to feel small in a bad way. I do not want you to feel insignificant. There is a kind of cheap nihilism that wraps itself around stories like this, that says, look how meaningless we are, look how brief, look how unimportant. That is the wrong response. That is reading the room wrong. The right response, I think, is something gentler and warmer and stranger, because look at what we did. A small species on a small planet in a quiet corner of a quiet galaxy. A species that, for almost the entirety of its existence, did not even know the planets in its own neighborhood. A species that only a few thousand years ago was still inventing the alphabet. A species that only a few hundred years ago did not yet know what other galaxies were. A species that less than 70 years ago had never sent anything into space at all. And yet, in 1977, this species, this small, clever, flickering species took a piece of plutonium, and a piece of copper, and a piece of gold, and the recorded laugh of a child, and the heartbeat of a woman in love, and the song of a humpback whale, and the Brandenburg Concerto and the Good Brothers playing rock and roll, and they bolted it all to the side of a tiny 10-sided machine, and they fired it up off a launch pad in Florida, and they sent it. They actually sent it out toward Jupiter, out toward Saturn, out toward the dark, out toward eternity. And the thing they sent will still be moving in a recognizable form long after every fact and feeling and language and person on this planet is gone, long after the earth itself is gone, long after the sun itself is gone. The most extraordinary monument our species has ever built, and we built it almost by accident, while trying to take a few photos of Jupiter's moons. That is not a story of meaninglessness. That is a story of one of the strangest, kindest, most quietly beautiful things any species has ever managed to do. To reach out, with the small means at hand, and put something of themselves into the long darkness and let it go. You are part of that. Just by being here, just by listening, just by belonging to the same kind of creature that built this small drifting machine and put a heartbeat on its side. You are part of the story. You are part of the species that made this. And when, somewhere in the next decade, the last signal from Voyager 1 quietly drops below the noise, and the engineers in Pasadena, some of them now very old, sit in their small office and say goodbye for the last time, you will be part of the goodbye too. Because the small machine that goes silent in that moment carries something of all of us. It carries the species that you are. It carries the longing we have always had to look up and to send something outward. It carries on its side the record of what we were, in this brief and tender window of being human. So when you hear in the years to come that Voyager 1 has finally gone dark, I do not want you to feel sad. Or not only sad. I want you to feel also that something extraordinary is now in its long phase, its real phase, its quiet, drifting, billion-year, 10 billion-year, trillion-year phase, the phase where it stops being a mission and starts being a monument, the phase where it stops being ours and becomes the universe's, the phase where the gold record on its side carries us, all of us, you and me and everyone we have ever known, gently, faithfully, silently, into a future none of us will ever see. That is where Voyager 1 is going. That is how far it can travel. Forever in the only sense the word can honestly mean. And in carrying us with it into that forever, it has answered a question we did not even know we were asking. Not how far can our machines go, but how long does the simple fact of our existence get to last? And the answer, thanks to one small spacecraft and one small gold disk, and one tiny act of cosmic generosity in the summer of 1977, is much longer than we ever dared to hope. Before I leave you tonight, one last quiet thing. If this kind of slow, deep, contemplative journey is something you find yourself wanting to return to, a quiet like or subscribe really does help. It is the small thing that lets me make the long things. And if you have made it all the way to this point in the dark, you are exactly the kind of listener I make these for. I am genuinely glad you are here. So now, breathe, settle, let the picture in your head come to rest. There is a small 10-sided machine drifting in the dark. It is 15 billion miles away. It carries a record of birdsong and Bach and a woman's heartbeat. It does not know it is doing any of this. It does not know we exist. It does not know what it is carrying. It is just moving, quietly, faithfully, in the same direction it has been moving for almost half a century. And it will keep moving, long after this video ends, long after you fall asleep, long after the morning comes, long after every morning we will ever see has come and gone. Somewhere out there in the dark above your roof, in the dark above your city, in the dark above your country, in the dark above this small blue world, Voyager 1 is moving. And on its side, a small piece of you is moving with it. Sleep well under the stars. Good night.